What's up, guys? Welcome to this little R session. The purpose of this session is just to build a little tool which is going to help you to maybe draw transition diagrams or check your answers if you've drawn them by hand. Okay, so there's no special computing skills required for this or any special theory. This is just writing a function that you can essentially use as a tool. And we're going to be using the igraph package. So I guess really the only preparation you can do is to go and read the package documentation for the igraph package. A little bit of which we do during this session anyway. So yeah, I hope you enjoy. Okay, cool. So let's see, what do we have in the template file? Okay, so first we have a goal. Write a function which draws transition diagrams for given transition probability matrix. Okay, that's what we're going to do. Task 1, call the igraph library and read documentation on the graph.adjacency and plot.igraph functions. Okay, so we're going to have to do a bit of reading, see what those functions are about, because we're going to use them to complete task 2. So task 2 is use the skeleton below to write a function which draws a transition diagram for a given transition probability matrix. You may use the graph.adjacency and plot.igraph functions. Okay. Use this function to draw a transition diagram for a Markov chain with transition probability matrix, and then I give you a large transition probability matrix. Let's check those columns. Yes, they sum to 1. Okay, and then I give you a function skeleton, draw underscore dot transition diagram. It'll take as argument gamma, which is just the transition matrix. And then there's going to be a bunch of things that we need to do. So first thing we're going to do is infer dimensions, round gamma to 2 or 3, name the states of the chain and apply blah, blah, blah. Next bit, create a matrix of coordinates for the vertices. Okay, so that's presumably for the plot. And then next, draw a directed graph with vertices at the above coordinates and directed edges according to the transition probability matrix. So that's actually where we're going to do the drawing. And then we're just going to return a network. Okay, whatever output we have from that function. Okay, so first thing, let's go. Library, igraph. Okay, so that just calls in library. And then we're going to go question mark. First thing we're going to check is graph.adjacency. Okay, so from this package, we're going to be using the graph.adjacency function, and from its help file we see it actually has a different alias, but in any case it takes an argument AG matrix, mode, what else is there, weighted, diagonal, add columns, etc. Okay, cool. So let's see what these arguments mean. So okay, so adjacency matrix, that's what it's for. A square adjacency matrix from igraph version 0.5.1. This can be a sparse matrix created with matrix package. Mode, character scalar provides or specifies how igraphs should interpret the supplied matrix. See also weighted argument. The interpretation depends on that too. Possible values are directed, undirected, upper, lower, min, max, etc. Okay, so presumably we're going to be using directed. Weighted, what does this argument do? This argument specifies whether to create a weighted graph from the adjacency matrix. If it is null, then it is an unweighted graph. It is an unweighted graph is created in the elements of the adjacency matrix, gives the number of edges between vertices. Okay, so that's just how that matrix is interpreted. If it is a character constant, then for every non-zero matrix entry, an edge is created and the value of the entry is added to an edge attribute named by the weighted argument. Okay, so that's probably what we're going to use. If it is true, so okay, you can send it just to a Boolean value, then the weighted graph is created and the name of the edge attribute will be weight. See also details below. Okay, diag. This is a logical scalar. Whether to include the diagonal of the matrix in the calculation. Okay, we'll be doing that because our transition matrix will include entries on the diagonal. And then add col names, character scalar, whether or not to add column names as vertex attributes or not. Okay, so that's just going to tell it. That's how we're going to, that's how we're going to label our states on the vertices. Okay. The other thing we need to check is plot.igraph. Okay, so plot.igraph is able to plot graphs to any R device. It is a non-interactive companion to the tk-plot function. Okay, they give a bunch of things there, but the thing we actually need to look at is this. So it has, under C also, it says layout for different layouts, igraph.plotting for detailed description of the plotting parameters for tk-plot and rgl plot, blah, blah, blah. Okay, so plot.igraph does a simple non-interactive 2D plotting to R device. Actually, it's an implementation of the plot generic function, so you can write plot graph instead of plot.igraph, graph, where graph is just the graph that we're going to construct. As it used the standard R devices, it supports every output format which R has an output device. The list is quite impressive. Okay, blah blah, a bunch of things. tk-plot does interactive 2D plotting using the TCLTK package. It can only handle graphs of moderate size. Okay, blah blah blah. Okay, so we can create interactive plots as well. Okay, but the important thing here is actually how to specify graphical parameters. So there are 3 ways to give values to the parameters described below in section parameters. We give these 3 ways here in order of their precedence. The first method is to supply named arguments to the plotting commands plot.igraph, tk-plot, or rglplot. Parameters for the vertices with the prefix vertex dot, parameters for edges have prefix edge dot, and global parameters have no prefix. Example, the color of the vertices can be given via the argument vertex.color, whereas edge.color sets the color of the edges. Layout gives the layout of the graphs. The second way is to assign a vertex edge graph. Yeah, okay, so we're not going to be using the second one, we're going to be using the third one. So essentially all that says is that if we want to, set graphical parameters for edges, we need to preclude whatever those parameters are by edge dot, and then the same for vertices. So vertex dot, and then set its color. So we want to set its color, we're going to be vertex dot color. If we want to set its frame color, vertex.frame color, vertex.shape, etc. And I guess, well, they won't all be cross-compatible, but yeah. Okay, so you can set edge.arrow size, edge.width, edge.color, etc. Okay, so that's just how we specify parameters for this function. Now let's get on to using it. Okay, so I'm just going to comment these out. And let's get on to task number 2. Okay, so I give you a transition diagram. Okay, so let's just run this, check that this... Okay, that works. Cool, then draw underscore transition diagram. It's going to take its function gamma. Right, so let's see. The first thing we need to do for this function is to infer dimensions. Okay, so that's simple enough. So let's just go u equals dim for dimension, whatever the dimension of gamma is. We're going to read off the first one. It's a square matrix. Okay, and that's going to tell us how many elements there are, or how many states there are. Next thing we want to do is round gamma to 2 or 3. Okay, so this is just so that when we plot things, you don't get long numbers. So let's make it 3. It's fine. So we're just going to reassign gamma to its rounded down to 3. Next thing we're going to do is name the states of the chain and apply to rows and columns of gamma. Okay, so we could have maybe included a parameter with names, but we're just going to use a generic specification. So let's go like col names for the column names of gamma, and set those equal to, we're going to create a sequence. And the way we're going to do that is by using the paste function. So paste will paste things together in R and create a text string. Okay, so we're going to paste, for example, state, which is just a text string. I'm going to create a space, and then we're going to I guess, prepend that to everything in a sequence running running from 1 to u. Okay, so 1 to u will be a vector. It's going to look at and say, okay, there's this state character vector or character, and it's going to paste those together and create a new vector. And then we can do the same for the row names. Okay, so call names, row names. Okay, just to show you what that does, let's just return gamma. Okay, so let's see what it does to gamma. Okay, so now you can see that the rows and columns have been given names, and you can also see that the matrix has been rounded to 3 decimal places. Okay, cool. So I'm going to take that out. Next up. Right, so create a matrix of coordinates for the vertices. Okay, so when we draw a transition diagram, we will have u vertices to draw. Remember from my little recipe, I say, you know, try and get regularly spaced points on a circle, so that'll create a regular polygon approximately. So how are we going to do that? Well, we need to find u equispaced points on a circle. Okay, so we're going to do that by first... yeah, let's create a sequence T running from 0, or actually we're running backwards, so 1 to 0 because we're going to go clockwise. Going 1 to 0, and we're going to create it of length equals u plus 1. Okay, so it's going to create u plus 1 points where they end on the same point, and we're only going to use the first u of those anyway. Okay, and then we're going to assign x and y coordinates, right? So how do we do that? Equation of a circle, just go sin 2 times pi times t. Okay, so 1's going to be the radius there. We can do the same for y. And we can just go, what do I say? And that should be cosine. Idiot. Okay, there you go. And then we're going to take the first u elements of that. Okay. And those are going to be the coordinates of our vertices. Okay, on a plotting plane. And now we need to collate those in a matrix of coordinates. So I'm just going to go capital X. And we're going to say that that is going to be C-bind. So remember, what does C-bind do? It column binds the coordinates. So we can say X equals X, Y equals Y. So it'll take those vectors and put them on the columns of that matrix. Okay, so X is going to be our coordinates. Okay, so let's just have it return X so you can see what it does. Okay, so how many states do we have? We have 6 states. Let's see what the coordinates are that it returns. Okay, so there are your y coordinates and x coordinates. Okay, yeah, seems quite regular. Cool. Next, what we want to do is we want to draw a directed graph with vertices at the above coordinates and directed edges according to a transition probability matrix. Okay, so how are we going to do that? The first thing we need to do is, when we use the igraph package, is we're going to have to sort of define what the network looks like. Right, so we're going to define something called net, and we're going to use the graph.adjacency to set up an adjacency graph. Where does it get that information? Well, it gets it from gamma, right? So gamma in this case is the adjacency matrix for this network, which it'll use to draw the transition diagram. Okay, what are the parameters we need to pass to that? Okay, we need to make it mode equals directed. Remember, there are various modes that we could have chosen. What else do we need to tell it? Is this a weighted graph? Yes, this is a weighted graph. What does that mean? Well, from the transition diagram, or from the transition probability matrix, the weights are given by the probabilities. So whenever it draws the edges, it'll assign the probabilities to those edges in the transition diagram. Weighted equals true. Diag equals true. So remember, we wanted the diagonals to feature in the calculations. If you don't, it ignores that. It won't draw those edges. Okay. And we probably will have non-zero entries on the diagonal of our transition probability matrix. And then add dot row names. Yes. Okay, so read the vertex labels off of the row names. You could have done it via the column names as well, of gamma. Okay, so remember that. Okay, so that's why we gave names to the column, rows and columns of the transition probability matrix. And we're going to say true. Okay, so that's going to create a network, and then what we want to do is plot that. Plot.igraph. Okay, and then we're going to plot what? We're going to plot net. So this is the network we created using graph.adjacency. Well, what else do we pass to that? Okay, so one of the things we already created was a layout. So one of the parameters for the igraph function is just give it a layout. So layout means here, give it the coordinates of the vertices where you want them to be. And we're just going to set that layout to X. Okay, so I'm just going to pass that for now. So that's going to be the only parameters. And let's see if it draws a transition diagram. Okay. Okay, and indeed it does. Okay, so it creates this nice 6-state diagram. Okay, cool. So, right. But that doesn't read very well. So, okay, we need to increase the size of the vertices. We need to change its color. The edges are gray. I don't think that's necessarily a problem. And it is not plotting the edge values. Okay, that's fine. Okay, so let's look. Let's change some parameters here. Okay, so next parameter, vertex color, vertex. Okay, dot color. Let's make the vertices gray 75, so light gray. Okay, so just for those of you who don't know, you can specify different grays in R, and you can just say gray. For example, 10 would be very dark gray, 90 would be very light, and anything in between. Vertex.color, vertex.label. Vertex.label, we're going to read that off of the v net.name. Okay. No, I guess it already did that anyway. But we can set the names from that. So v is applied to net. It extracts the names from the rows, I guess. Vertex.size. Yes, we want to increase that. And we're going to make it 50. So I think I played around with this. Okay, so let's see what that does. Okay, cool. Yeah, that increases the size of the nodes or the vertices, makes for a better plot. Okay, what else do we need? Edge.curved. Okay, yeah, cool. So the edges I have here are all like straight arrows, and that's not necessarily what we draw by hand. Typically what we draw by hand is we'll draw all of the arrows out of each one state. So what's happening now is when there's back and forth between any two states, you'll see that it's just two arrows on top of each other. Like for example, states 4 and 5 and so on. Okay, so that actually makes it more difficult to read. So the way we're going to fix this is we're going to say edge.curved, and we're going to make the curvature 0.2. So let's see what that does. Okay, so now it separates those, and I guess we can you can increase that if you want to. Let's make it 0.4. Maybe that's a bit much. 3. Maybe even that's too much, but whatever. Let's make it 0.25. Okay, so 0.25. Edge.label. Okay, so this is where we're gonna add labels to the edges. Edge.label, what we want to read off is go on the edges. So we're going to use E, that's another function, and extract the attribute weight. Okay. And then it plots the probabilities as well. Okay, cool. So it's starting to look good for our transition diagram. Maybe another thing we want to do is set the edge color. So edge color, and we can set that equal to black. And then another parameter that I specify is just margin. I set it equal to, so that the plot takes up more of the actual plotting space. So you can see it's a bit offset there from left. Does it change? Ugh, what did I do now? I'm missing a comma. There you go. Okay, cool. Okay, and then maybe another thing I do, oh yeah, so for example with states 3 and 2, you'll see that the loops there, the loop from state 3 back to itself, it's sort of overlapping with some of the other edges. So when we plot things in a circle like that, that's always going to happen. So one thing I can do, edge dot loop dot angle, is I can make that minus pi divided by 4. Okay, so that just angles those loops up. Okay, maybe another thing we want to do is, okay, we see that it starts state 1 off on the right. Maybe you want state 1 to be up top. So one thing we can do is maybe add, yeah, let's add a quarter to t up top here, and then that will rotate the graph slightly. Okay, so 0.25. Okay, that puts state 1 up top. Okay, and now we have a function which can draw transition graphs. So if you want to, you can use this to check your answers when you're drawing transition diagrams for whatever transition probability matrices I give you. Now, as a bonus, what's cool about this package is you can actually make this process interactive. And the way you can do that is by the tkplot function. So earlier, I think we read that, so plot.igraph does simple non-interactive 2D plotting, blah, blah, blah. And then they had this other thing called tkplot, does interactive 2D plotting using the whatever package. It can only handle graphs of moderate. Okay, that doesn't matter. We've got plots of moderate size. But essentially what's cool about this is these functions take the same parameters as does plot.igraph. So if you wanted to make this interactive, you can just use tkplot, take plot.igraph, and replace that bit. And then let's see what happens. Okay, so let's do this. And it should pop out a little window. And what's cool about this window is now you can interact with the graph. So let's say maybe I use Etienne's formula, I get a graph, I can't really read it well, so let's maybe increase the size of this thing, give us some more space. So maybe I'm not happy with state 1 there, I can move it around there. Okay, let's maybe move states 2 and 3 down here, see what's going on. Oh, these are overplotting a lot, so maybe I can, I don't know, move them around like that little group. Whichever way. But yeah, this is also a cool way to sort of see how things are connected and or not, just by like, sort of perturbing these or moving them around. But yeah, so yeah, I guess that's that. Hope you enjoy playing around with this function and actually use it. I find it very useful because I'm too lazy to draw these by hand. So yeah, I guess that's that, and I'll see you in the next one.